of this plenary session on emerging Earth observation capabilities for developing metrics and indicators to monitor environmental policy. It's a shame we didn't find a more snappier title, isn't it? Because that doesn't quite roll off the tongue. But it's looking forward to 5 great presentations. These ones are going to cover some slightly different themes to the first 4 we saw in the first session. So looking at agriculture, soils and water and air quality from a range of different kind of variations on those themes. So without further ado, I'm going to introduce the first presentation. So this is around the development of national scale digital farmland observatory for looking at crop traits and derived from Sentinel-2 and ProSail biophysical parameters. So without further ado, welcome Feng Yin from UCL and NCEO to come and bring that presentation.
Thank you. Yeah. Hello, everyone. My name is Feng. Today, I'm going to present some works that we have done for the BBSRC Zero Plus project. And in this project, we mainly do the trying to develop a UK digital farmland observatory by the use of Sentinel-2 observation. So the requirement for the digital farmland observatory is to provide comprehensive information, describe the agriculture productivity and emissions and other things for all the farmland over the entire UK. And what Sentinel-2 can offer to us is especially got spatial bands covering visible to shortwave infrared that's suitable for the vegetation monitoring, and also got 10 to 20 meter spatial resolution, which allows us to do the field level analysis. And it got 2 or 3 days repeated coverage over the entire UK. And there are plenty of studies showing that we can do crop yield or biomass estimate with the observation dataset. So the satellite data only provide us with the reflectances or radiance, but we want to convert this information into something that more related to the crop in the field. So here we use the canopy radial transfer model, ProSail, which compose a leaf model and a canopy model. There are parameters which describe the leaf property and also parameters describe the canopy properties. We call them biophysical parameters. And by use the ProSail model and change the parameters, we are able to simulate different radiance or reflectances of the for different sensors. And in the early test, we simply did a training from the model output to the model input. We call them inverse simulators. It works okay for the sensitive parameters such as the leaf area index, but not so well for those ones that are not well constrained. And so to be able to get more robust estimation of those biophysical parameters, we we did a big data analysis by taking a lot of samples from the US Corn Belt and Northeast China. And we take the time series of surface reflectance over those Sentinel-2 tiles, shown on the top of the plot. And then we did some, we ran the inverse simulators for all the samples. And then we normalize the time difference between the samples. And we end up with something very clear patterns of biophysical parameters changed over time. And so this basically gives us a first order model where we call them archetypes, basically the mean or median of the biophysical parameters. And after getting the archetypes, we simply can scale them up and down for the magnitude and also shift them over time for the different phenologies, which basically simulate different crop growth conditions of the crops in the field. And then we run through the ProSail model. We can simulate the different kind of satellite reflectance And then by combining the satellite reflectance, select the ones that the trajectories of reflectance that fit well with our observations, we are able to narrow down our estimation for the biophysical parameters. Where in the bottom right, we show the our retrieval of the archetypes, and also we show the inverse emulators retrieval, where show as dotted dashed line, which is quite noisy, but the archetypes are very clean retrievals. So then we run the validation over the overnight field over Munich for different kind of probes, and here's the validation of the biophysical parameters over time. So they did measurements of leaf area index, chlorophyll content, leaf brown pigment content, and also leaf water. It's okay for the results of the retrieval are quite highly correlated with ground measurements for the leaf area index, chlorophyll content, and the brown pigment, but it's more complicated for the results for the leaf water, where we can estimate the leaf water pretty well in the early season, but not be able to resolve very well in the end of the season, and we're still looking into why that happens. And our colleagues also did some measurements of the hyperspectral reflectance measurements in the field, in 4 of the fields, and then since we have run the retrieval over all the pixels within those fields, so we can forward simulate the hyperspectral reflectance and compare it to the ground measurements. We also have a way to verify our retrieval. And this is the result. Basically, we go time series. In the middle is the NDVI, and then we did the measurements of hyperspectral measurements for different dates across the whole growing season. And then for most of the time, our forward simulation with our retrieval agree pretty well with the ground measurement. This is a nice example for the maize. It's okay for most of the cases, but not so good for the ones that have a large variation in the ground measurements. This is because they have a larger uncertainty in the ground measurements than our retrieval. And then this more quantitative estimation, a comparison of our retrieval against the ground measurement, pretty good without high correlation, and with RMSE around 0.04 across the whole spectral region. And so after that, we done the verification of the archetype retrieval. We then did a demonstration of application of the archetype. We tried to use the archetype retrieval to predict the county level yield across the US Corn Belt for 2017 to 2020. And where we show the yield map on the right-hand side, which broadly there's a higher yield in the central Corn Belt, but lower yield across the all the borders edges. But there are also interannual variability of the yield across the counties. So then we run the archetype retrieval for each county with samples, with thousands of samples. And then we average the archetype retrieval to represent each county. And also we use the, we take the weather information from the ERA5 or reanalysis datasets, because people normally use the weather information for yield analysis. And this is simply we did, on the right hand side is basically the average of weather information on top, and then the archetype retrieval. And then we did a simple correlation analysis between our weather information and also archetype retrieval to the county level yield. And so on the left hand side, that's a polar bar plot where the longer the bar and the darker the color means the higher correlation. You go the leaf area index magnitude is highly correlated to the final yield, but also the other parameters such as the leaf angle distribution, temperature, and phenology parameters are also quite important. Since there's a very strong correlation between the parameters or yield, so we did a simple empirical yield prediction model. One is the ordinary least square, which is a linear regression model, and the other one is X-tree regressor. It's a very similar to the random forest, and as expected, the nonlinear one got better accuracy with an R value around 0.91. Which explains the yield variation around 82%. But we also did analysis with without using the weather information on top, where they actually show very similar results to the ones with the information, which means that the actual Earth observation contains most information that you needed for the yield analysis, yield estimate. And then we also show the feature importance on the left in the polar bar plot. And then the most important parameters are the leaf area magnitude and also the thermal timing or phenology parameters. And then finally, we did some county, we left out some counties for the training and validation, and just to check the interannual variability of the yield. So for those six counties, we for most of the cases, the model can the empirical yield model can capture the interannual variability of the yield pretty well. So yeah, finally some summary, and I think it's very promising to do the crop monitoring with Earth observation, and but it need very careful treatment of the data process, and also the benefits of the big Earth observation data is yet to be discovered. We can do very accurate estimation of yield estimation with only Earth observation data, and we want to have more ground measurements of biophysical parameters and yield for us to verify our result. And also in the end of the project, we want to deliver around 200 terabytes of data sets for analysis rate data set, and also the biophysical parameters. And the improvements is basically we want to maybe incorporate stress and also improve the structural representation in our radiation transfer model. Thank you.
Thank you, Feng. Thank you, Feng. We've got a couple of questions on Slido. So let's try and answer those. So Feng, how do crop traits differ across major crop types at large scale? Could measurements of crop traits be useful in useful input features in discriminating different crops? Is the first one.
Yes, I think the biggest difference of the crop traits for different crops, I think, is mainly the timing. So, which is actually what people normally use for the crop classification is you use time series of the observation. It's got better results than using any single image, which basically bringing the timing information. So I think the biggest difference I observed by running this kind of archetype retrieval over large regions is that the timing for different crops are quite different. Yeah.
Okay, thank you. And then another question on Slido. Would improvements in spatial resolution of the Sentinel-2 Brfs lead to higher correlations? I presume S2 is Sentinel-2, but I may be wrong.
Lead to higher correlations. So what higher correlation to? Sorry, yeah.
If somebody's asked that in the room, I mean, if they could provide some expand on that or clarify for Feng, that'd be great.
Yeah. I think maybe it's yeah, I think because the people also use coarser resolution for the yield analysis and those biophysical parameter retrieval. I think probably the Sentinel-2 have more spectral bands, and you have a less contamination from soil or other objects, non-vegetation objects, and helps to give you a higher, more cleaner signals, which help you probably improve the correlations in both the biophysical parameter retrieval and the yield estimation. Yeah.
Great, thank you, Feng. I won't ask for any questions in the planetarium at the moment because we've got 15 minutes for discussion at the end. So thank you once again, Feng.
Thank you.
Great. Our next presentation is around monitoring smallholder maize in northern Ghana. This focuses and will present a data set to support the development of crop yield monitoring, and to present to us is Jose Gomez-Danz from UCL. So Jose, I'll hand it over to you.
Thank you. Thank you, everyone. So this is a talk that basically continues with the previous speaker was presenting. He's also a co-author of that, of basically using satellite data to monitor crops, but rather than actually doing it in the States and in the Northern Hemisphere, we're basically looking at subsistence smallholder farming in Africa, which is a completely different kind of thing, and we're also sort of doing things in a slightly different way. So we're looking at maize in northern Ghana. It's a staple there. It sort of supports a lot of the population. It's a rain-fed crop grown in a very sort of heterogeneous way due to sort of management variations and non-professional farmers, and usually it's recognized that the attained yields, the yields are actually sort of the production of maize is actually very well below their potential. So there's a potential to increase the production of grain. As this is such a heterogeneous system, there's a huge uncertainty of production, where it happens, when it happens, and how much of it there is. And there's a great interest in actually monitoring this. And basically, Earth observation is a pragmatic way of going about this. We choose northern Ghana, but probably what we learn about this can probably be extended to other areas of West Africa or even other smallholder places in Africa. So what we'd like to do is do an Earth observation based monitoring system, and that has a number of pieces that go into it, and we're going to look at some of them and just sort of list them. First thing we need is to know where the crops are, and this is extremely challenging for these kind of scenarios, because the crops are small, they grow on the rainy season, everything grows at the same time, and usually you have persistent cloud cover. So we're still in the infancy of these crop maps, and we're not really able to sort of provide the same sort of information as you would get in Europe or elsewhere. Meteorological data and soils data, they're probably okay, pragmatically. And what we want to do is we want to interpret these inputs in terms of crop development, and then we basically get the crop development indicators observed by the satellite, and that basically allows us to sort of put all this kind of information together. For that, we need models. We have sort of crop models that basically describe processes like photosynthesis and so on. And the idea is that we run this with our meteorological data, predict something that the satellite sees. In this case, it's the amount of leaf area, and we compare that with the leaf area from the satellite. And one thing that you have here is this lack of validation and training data that is an important part of having confidence in what's going on. So a pragmatic response to these issues is to prototype on a small typical area and gather loads of ground data. You can basically see some this is basically the yields that was measured over some fields, and it's a huge distribution over an area that is basically weather, with constant weather. And we collect all these data, and then we defined a way of linking the observations and the models by a very simple data assimilation scheme that scales spatially. We use a published crop growth model, and we use these available global data sets. So the Earth observation data, ideally you'd like to use Sentinel-2 as it was shown before, but actually what you see here is a time series over the growing season from last year. There are huge gaps because of persistent cloud. But if you then get the planet data, which is commercial and available, you get pretty much the same signal and a lot of temporal sampling. So we decided to go for that to derive our LAI. Planet doesn't give you LAI, so we have to derive it ourselves. And the way to go about that is complicated because the cloud mask and the cloud shadow mask from Planet aren't great. So you have to do a bit of outlier filtering and feed a couple of functions to basically come up with a simple transformation from the vegetation index from Planet to the LAI. We don't use complicated radiative transfer models here as in the previous talk, because with the planet data, they're a bit overkill. And this is the validation, and the results are modest. We have a sort of underestimation of the higher LAI, but the RMSE is about in line what you would expect for this kind of product, and there's no bias. So about the crop model, we use the waffles crop model, and basically what I'm showing here is the space of maximum LAI versus yield. And the idea here is that you see those gray dots there are basically our ground measurements, and basically the model basically encompasses our data. We're changing 4 parameters here: the sowing date, the initial grain mass, the leaf lifespan, and the assimilation efficiency. And those parameters basically modify the LAI trajectories, but also the accumulation of biomass. We also, rather than using the estimation of yield from the model, we use estimation of ground biomass, because yield is quite a complicated process in maize and has different stressors. So this has been widely used, and usually what people do is they take a fraction of the above ground biomass and say, right, okay, 70% of it is yield. But when you look at the ground data that was collected, we find that if you do this calculation, this 70% actually goes from around 20% to 80%. So a single number will not work. It's another kind of parameter that is that you have to vary. So what we do is we develop a very simple sort of model where we fit the LAI, we got the ground data, and we try to estimate it. It's just a linear model, The assimilation scheme is broadly based on a particle filter formulation. It assumes Gaussian statistics, a uniform prior, and we just basically sample this crop growth model over the parameter space, and I create this ensemble. This is done at a coarse resolution, but it can be actually used for millions and millions of pixels. So it's a very efficient way of dealing with the assimilation problem. This is how it works. These are the observations from planets. So you see we got loads of them at the end, but we actually got some gaps at the beginning of the growing season. That's the prior distribution, more or less uniform. And then what we do is we match the model trajectories to the observations, and we are basically selecting and calculating our posterior distribution. With our posterior distribution, we can also calculate our posterior above ground biomass, and then solve for our yield conversion. So finally, some results. And these are the 3 different ways where we convert the 3 different schemes that we have for converting above ground biomass predicted by the model to yield. And basically it's a full linear model, an offset term, or a harvest index kind of concept. And the harvest index, as expected, is the worst. We know that a single value will not work here from the ground evidence. The other 2 are pretty similar, but in this case, this one it seems to be over-parameterized. There's a strong correlation between the 2 terms. So basically, we go with this offset. This offset kind of suggests that there is like a minimum viable biomass in order to get yield. That seems to be the physical explanation of this. We also get sort of details for every pixel. So this is at a resolution of 3.5 meters or 4 meters kind of scale. And this is basically, you're looking at 4 fields at the top. That's the yield. You can basically see it's very heterogeneous even within the field. Okay, so this is a really complicated kind of scenario where all the agriculture is maximize, fertilizer, irrigation, and things like that. None of that is happening here. So you've got massive variation within the field and across fields. We also see that the patterns you see in the yield are very similar to the maximum LAI, and that ties in with the kind of study that was presented before by Feng. That there's a lot of information in the LAI relating to yield. It's a data simulation system, so you've got some uncertainty on the yield estimate, and we also have the parameters, which we were hoping we could use as diagnostics. We know that the yield is lower here and higher here. The model actually explain in terms of parameters why that is the case. Well, it seems that there's not really a good, clear relationship, a nice story that I can tell. And probably this is because there's some sort of equifinality here. This is a posterior correlation matrix. So that's the correlation of 1. The size is the amount of the correlation, and black means negative correlation. So there's really strong negative correlations, compensatory effects between these parameters. And that basically means that you cannot just look at one parameter, you have to look at the whole thing to understand what's going on. So just to quickly finish off, smallholder croplands are very heterogeneous. That has implications for how we study them. Earth observation is definitely a tool you need to understand these huge variability. These local variations are, as a consequence of that, these are not really taken into account by crop models. So this is an area that's sort of suffering changes in the rain regimes due to climate change, and there's a huge population there. So when you basically look at sort of future projections and things like that, the use of the crop model has to be a bit more sophisticated to deal with this huge variation. As I said, the idea that we have this project is collaborating with our colleagues in Ghana, is to basically set up something that is sort of simple and pragmatic, that they can basically sort of take forward and start sort of working with. And the results are sort of modest in terms of the prediction ability. We don't explain them, a huge amount of the yield variation as shown in the previous talk, but actually it is actually comparable with similar studies that people have done in other places. And being a starting point, I think that is quite positive. And yeah, there's one of the biggest things missing here is sort of ground data, understanding what's actually going on with the crops and everything. And for that, working with the people who have their feet there on the ground and are not sitting in front of a computer all day is definitely a requirement. So I have my list of acknowledgements here. I leave it here. Thank you very much.
Thank you very much. Thank you very much, Jose. We've just got probably time for one question here. So we have got one on Slido. So that is PlanetScope data have much poorer radiometric calibration of Sentinel-2. Will this have any impact on your retrievals?
Yeah, we find that there were actually one of the things is that you haven't got Sentinel-2 data here because of clouds. So if we had Sentinel-2 data, we would definitely use it, but actually that's not that's not really possible. And there's two things about these about the things. It seems that the patterns that we find from Sentinel-2 and whenever we can get it and Planet are actually quite similar. So it looks that radiometric calibration is okay. There's a big uncertainty but on the Planet data, but you compound that by having lots and lots of observations. So there doesn't seem to be any big biases there that are hampering things.
Thank you, Jose. Thank you. Great. The next presentation sees us move on to monitoring for soils and water. And let me invite Martin Unwin, Principal GNSS Engineer at SSTL, to come and present to us about hydro GNSS and how that can help us in our indicators on groundwater and soil. Thank you, Martin.
Thank you very much, and thank you for attending. So yes, I'm going to be talking about climate variable sensing from the Hydro GNSS mission. I'd like to acknowledge a whole team of co-authors and the science team that works with us, including Sapienza, Tor Vergata, FMI, IEC, NOC, Nottingham, TUV, and of course ESA and other colleagues at SSTL. So first of all, to talk about a little bit about the European Space Agency SCOUT program. So this is a new initiative from ESA's Earth Observation Directorate, and its focus is on small satellite missions, demonstrating that you can achieve science with a small budget and rapid schedule. So the missions are fully funded by ESA, and it's characterized by an agile, low-cost development process to prove new concepts for future ESA endeavors. And the aim is to tap into new space approach and achieve a launch within 36 months after kickoff and a budget of under 30 million euros. So that involves managing the higher risks of the small satellite, small space approach, use of COTS components and reuse of existing designs, lower cost and faster to service. So the aim behind this is to give free, full and open data, and it's delivered using a service-based approach. So the mission was selected as one of the first 2 SCOUT missions. There were something like 16 proposals, and HydroGNSS was selected as one of the first 2. And the project was kicked off just under a year ago in October 2021. And now a bit about the technology that's used. So this is Gnss Reflectometry. And the idea behind this is to use the signals that are being broadcast by GNSS satellites, that's GPS and Galileo and others, that are being broadcast all the time. These are L-band signals. There's over 100 sources of them in orbit. And to use that as a radar source. So it's a kind of low-cost radar where you don't need the transmitter. You just need the GNSS receiver on board. So it's possible to host on a small satellite, and it's possible to run with 100% duty. So there's been a long list of, it's been a long process to get to this point. We put together the first ideas back in 2000, and we flew an experiment on UKDMC, which grabbed the bits and showed that it was possible. This was SSTL partnering with National Oceanography Centre. We're able to show that there was a dependence. Not only did we pick up reflections over all surfaces, there was a dependence on the roughness of the ocean. So if it was a windy wind over the ocean, you get different response to if it's calm. And so that led on to the Tech Demosat-1 mission. And shortly, and overlapping with that was the NASA Cygnus, where we provided 8 payloads for the constellation that measures hurricanes. And then more recently, DOT-1 and now HydroGNSS. So the early work showed that you can use it for ocean wind and wave sensing. You can use it for sea ice extent and ice concentration. And you can use it for land sensing. And that is what we're addressing with HydroGNSS. So many of you know far more about this than I do, but obviously hydrological knowledge is very important. Water is the natural resource that's vital to climate, weather, life on Earth. And it's present on or in land in the form of soil moisture, wetlands and rivers, snow and ice, vegetation. And the World Economic Forum identifies the land water related issues as amongst the greatest challenges facing the population for the future. And the soil moisture is vital for weather, agriculture, storage in land, subsidence. And the freeze thaw is vital for permafrost, which affects methane emissions, has a significant climate impact. Inundation affects flooding alerts, it affects wetlands we heard about earlier, methane emissions and biodiversity, and biomass affects the carbon stock. So models need measurements of these for understanding predictions and planning for the future in tackling climate change. So Earth system models need measurements such as these for climate prediction, and on an operational basis, numerical weather prediction need these for weather. And it allows us to monitor actions that are taken from COP26 and future pledges as we try and tackle climate change. So SCOUT is targeting essential climate variables. There's 54 of them, but HydroGNSS is targeting some 4 variables which are closely related to ECVs. So there's soil moisture, freeze thaw, inundation, biomass, and there is evidence that GNSS reflectometry can address all these ECVs gathered from studies using TDS and Cygnus data. We don't go into details in this presentation, but there are links elsewhere which talk about this. Uniquely, L-band offers forward scatter reflection, which means that you can sense inundation under vegetation canopies. So this is an animation which shows the concept of the targets that we're going for: the freeze thaw over permafrost, biomass, soil moisture, and inundation. And the way this is done is we're using signals from GPS and Galileo satellites, which are high altitude, or medium Earth orbit satellites. And these are transmitting all the time, and our satellite is in a low Earth orbit, and it's picking up the reflections of these off the specular points. And you end up with things called delay Doppler maps there in the bottom right, which contain the information about how well it's reflecting, how rough the surface is, what the dielectric constant is. And this works over all weather. It works because L-band penetrates the land. So we're targeting soil moisture and wetlands, the biomass, and we're targeting freeze thaw, particularly over permafrost. And we have secondary products over the ocean and ice extent, so we can measure wind speed and ice coverage and concentration. So with two satellites, in our original proposal, we proposed two satellites. The coverage builds up. It's a quasi-random thing because it's dependent on the location of two satellites. But over 15 days, we cover the whole globe with two satellites. So coming on to what HydroGNSS addresses, it addresses a niche in application. So this is a spatial temporal diagram. With one satellite, we can get about 10-kilometer resolution, but potentially with the coherent channel that we're promoting, then we can get down to higher resolution. And by adding more satellites, the HydroGNSS Plus, then you can get down to a higher temporal resolution. So you need to add more satellites, and you can see where it sits in the scheme and how it applies to the for hydrology. So just a few words on the instrument and mission. So it's an instrument that's based on the instrument we designed for TDS-1 Cygnus. It's got a 13 dBi nadir antenna. It's dual frequency, dual polarized, and it's supporting new measurements, including Galileo, coherent channel, dual polarization, dual frequency. It's a 65 kilogram microsatellite, highly accurate attitude determination with star tracker. It's got propulsion. The mission operation and the payload data is located in Guildford. We're using Svalbard to give us short delays from delivery of the data. And we're working closely with our science partners in putting together the payload data ground segment. So initially we're funded to provide a single satellite. There is an option for a second satellite, which we are busy discussing at the moment, but more satellites can be added to improve the temporal resolution. The progress is going well. We had the kickoff last October. We had the preliminary design review, May, June. We're heading into the critical design review now. The first hardware is appearing. We have engineering models, and we're trying to achieve technology readiness level 6 on all systems. And we're making progress with the payload. It's a complex antenna, trying to do the L1 and L5 in dual polarization is very demanding. We have very low noise amplifiers provided by EECL. And we're developing the signal processing and achieving all the TRL6 goals that we're aiming for. And we're making progress with the ground segment. We have an end-to-end simulator operational, and it's verifying the level 1, level 2 processes. And we have partial validation against some of the data we have in orbit already. And we've signed up for the launch. So we are going to be launching from the summer 2024 with a rideshare launch. And this is quite to finish up a couple more slides. This is a low-cost approach to fill a potential gap that's arising, that we have SMOS and SMAP satellites in orbit measuring soil moisture as a coarse resolution. and they are very widely used, but they are both past the end of their life, so they are both at risk. And there is potentially a gap coming before the high priority Copernicus missions, such as SIMA, where we lose measurements from SMOS and SMAP. And just to compare it to typical other satellites, the Hydro-GNSS is around 65 kilos. The budget for 2 of them was around 30 million euros. If you compare that to, in particular, NASA SMAP, that was a 1-ton satellite, $1 billion. It's very highly prized for its measurements, but it's been operating beyond the end of its life. And things like SIMA are going to be big satellites. So it is possible to address this with, in some cases, small satellites can take valuable measurements, and it allows you to build constellations because they're not too expensive. So to conclude the presentation, Gnss Reflectometry has been established thanks to the work we did on TDS and thanks to Cygnus. It's an important Earth observation technique. The World Meteorological Organization identifies the need for Gnss reflectometry in its vision for 2040 WEGOS document. 1 or 2 Hydro-GNSS satellites addresses ECVs with good spatial resolution. It's reasonable coverage at high latitudes where freeze thaw and biomass slowly varying, and boreal forests and disturbances can be measured where the ESO biomass mission cannot operate. However, moving on to 8 satellites, it would provide much better revisit time and improved temporal resolution. It would give coverage similar to SMOS and SMAP, and it offers secondary measurements of ocean, wind speed, and ice extent. And it's a sustainable approach, using small satellites for sensing weather and climate as we continue to tackle climate change. And that's the end of my presentation. Thank you.
Thank you, Martin. That was a really fascinating presentation. We do have a couple of questions, again on Slido. I think we might even have time to take one from the room. Will Hydro-GNSS be able to detect and measure sea ice extent and ice water content for ice sheets and glaciers, or is it specifically for permafrost monitoring?
We are using similar settings to what we used on TDS, and that has been used to measure the melt. It demonstrates the melt on the Greenland ice sheet, and it has been used to measure ice extent. It may not be optimized for it, but yes, it should be possible to use it for that purpose.
Great, thank you. And then another question on Slido. How many GNSS R satellites would be needed to generate coverage comparable to SMOS or SMAP? Yeah, and I think I should say here that it's not quite the same thing. It's doing things in a different way. It's measuring it slightly differently. It gets a slightly higher resolution than SMOS or SMAP, and it's measuring forward scatter. But roughly, to get the same kind of coverage, we reckon a constellation of about 8 satellites would be similar to the coverage of SMOS or SMAP. Okay, thank you. And then another question that's just come in. Other sensors like ASCAT, soil moisture use, change detection, will Hydro-GNSS use this approach or one-pass retrieval? Well, we have. We're fortunate to have several science partners working with us who favor different approaches. So we have Sapienza is using one approach, 2 approaches. They have 2 possible approaches, and we also have a applied neural network approach that's being used by Emanuele Santi in IFAC. And we're also partnering with Wolfgang Wagner, who uses I think the high and low method as well. So we have a number of approaches. I think we're still settling which ones are going to be rolled out for the product delivery. But we are aware that there's more than one way of doing this. But we will be releasing the level 1 data. So if people want to develop their own products, they can do that as well. That's great. Thank you very much, Martin. Next, we're going to move on to air quality, and our next presenter is Edward Grisbeard from Imperial College, and he's going to talk about towards ship sulfur emissions monitoring in cloudy skies. So thank you, Edward.
Oh, thank you, Keith. Yes, so I'm going to be talking about some of the work we've been doing looking at ship emissions. Now, a lot of my work actually is looking at clouds, which is a little bit different to what people have been doing here in the past for understanding how clouds behave, but that also tells us something about what the ships are up to as well. So ships emit sulfur, and particularly sulfur dioxide and sulfates across the global oceans, often in populated coastal regions, but also in the middle of the open ocean. And shipping sulfur as air pollution is responsible for large numbers of premature deaths and cases of childhood asthma, as well as significant amounts of acid rain, particularly in remote locations. Now, as cargo volumes continue to climb, so do ship sulfur emissions, with some small blips due to the pandemic. Now, because of this, the International Maritime Organization has been focused on regulations for ships to try and reduce the amount of sulfur emitted by ships. So we have these coastal local emission control regions around Europe and North America, where ships have to burn low sulfur fuel. And since 2020, there have been regulations across the global ocean requiring ships to burn, again, low sulfur fuel. Now, there are strong financial incentives for non-compliance here. Fuel at the moment is relatively expensive. These are some kind of indicative costs for standard fuel oil. But if you look at the relative costs for the low sulfur fuel oil, it's clearly much more expensive. Burning low sulfur fuel oil is expensive. And so in the open ocean, we'd really like to be able to know whether ships are actually complying with these regulations and burning the more expensive fuel. Now, Sentinel-5 and Tropomi give us some ways of looking at this in clear skies, but a lot of the planet is covered by cloud, up to 60%, 70% at any one time. So how do we monitor those regions that are cloudy? Now, obviously, because I look at clouds, I'm going to tell you that the answer here is actually looking at the clouds to understand what these ships are doing underneath them. Now, when ships burn high sulfur fuel, they release a lot of sulfur dioxide, which then gets oxidized very quickly into particles called sulfates. And these then modify the clouds. So these lines in the cloud here that we can see are clouds that have been modified by ships, cloud formations we know as ship tracks. They typically have an increased cloud fraction, so you get more cloud in this polluted region behind the ship. The droplets in the cloud are often smaller as well. So you can see these yellow regions here are cases where the droplets in the cloud are smaller, because you have more droplets, because there are more particulate pollutants. Those droplets are on average smaller because you're sharing the same amount of water out across these droplets. Now, because the droplets are smaller, it means this shows up very clearly in near-infrared imagery. So you can look at this image here. Okay, you can kind of see it. This here is a false color image of the Northeast Pacific. So this is the coast of California along the bottom here. So north is off to the right. You can kind of see Monterey Bay in here. Los Angeles is down here. But the important part are these thin green lines up near the top. So those lines are where the droplets are much smaller. These are those ship tracks. So each of these lines is formed by a ship emitting pollutants into that cloud. Now we can zoom in a bit further, and we can add in the ships first. So these thin black lines then are the estimated locations of the ship pollutants, with the dots being the ship locations. If we zoom in a bit, you can see that a bit clearer. And what this enables us to do, we can see that these thin black lines typically line up with these ship tracks. What this enables us to do is say, here is a cloud that's been modified by ships, and we know which specific ship caused that change in the cloud. Now, if we look at where these tracks occur, just in the Northeast Pacific for the moment, we can see that kind of in 2003, they kind of occurred pretty much everywhere. There's a slight peak close to the coast, but in general, you find them all over the place. As we move into 2014, the pattern changes slightly. So we have more tracks, particularly along this kind of line here, which is the kind of main shipping route between Panama and China and Japan. So we have more ships, more ship tracks. In 2015, the number of ship tracks close to the coast basically completely disappears. So inside that red line, which is the 200-mile limit of US and Canadian waters, ship tracks now no longer occur, or almost completely, they're kind of almost completely gone. And in 2016, that continues, and that continues right to the present day. Now, 2015 was the year when the US and Canada introduced coastal emission controls. So the sulfur content of the fuel went from about 2.5% on average to less than 0.1%. So by reducing the amount of sulfur in the ship fuel, you reduce the amount of particulates the ship emits, and so you change how likely it is to modify the cloud above it. And this, this effect is particularly strong. You can normally, if the projector is, you can see this change in individual clouds. So in 2003 on the top plot, you can see a lot of these lines kind of relatively close to the coast and also somewhat outside it. As we move into 2015, you can still see these lines kind of outside and further away from the coast. So this is California again. This is the 200-mile limit. And here are some of those ship tracks outside the 200-mile limit, but inside the 200-mile limit, they're just completely gone. Now, we know there are ships there, and we know that cloud is sensitive to these particulates. You can see this kind of blob here as pollution from San Francisco changing the cloud. So we know the ships are there, but they're burning clean fuel, which reduces their impact on the clouds. Now, we can do something a little bit more qualitative. We can look at these individual tracks, kind of look at their properties and the properties of the cloud surrounding them, which then tells us how strong the ship impact on that particular cloud was. And so what we're looking for is the kind of droplet number concentration in the track compared to the numbers outside, which gives us then a kind of enhancement factor for how many more droplets there are in the polluted region of the cloud. And if we do that, we can make an estimate of kind of what that enhancement factor should be based on the background cloud or the kind of unpolluted cloud and our information about what the ship is doing, what ship emissions are. And we can fit that observed enhancement factor pretty well. So we have a reasonable idea of what the ships are doing, how the cloud responds, and we can then go backwards, right? So we can say, given an observed enhancement in droplet number, what kind of sulfur emissions would we expect from that ship? Now, the black dots here are the interesting ones because they're in clouds that are relatively clean. And we see actually a pretty good kind of agreement between the kind of parameterized or the emissions estimated from the ship based on our knowledge of the ship, how fast it's going, what kind of cargo it's carrying, and those retrieved from these changes in the cloud. We actually have some outliers here as well. Those two dots down towards the bottom with kind of green rings around them were cases where we identified that this parameterized emissions or the ship emissions model wasn't actually working correctly. Now this, we can do this off the coast of California, but if we like to extend it globally, it's a little bit more work. Doing this by hand takes a long time. And when you've got a kind of billion locations of kind of every ship in the global fleet every half an hour across the globe, it takes a long time to do that by hand. So obviously we get the computer to do it, and we train it to identify cases where we know there's a ship. We can look at the satellite image or the near infrared image and say, is that ship generating a track? We've got a selection of cases here across the top where the ship was not generating a track and cases down the bottom where it was. So the sulfur emissions are strong enough to modify that cloud. Now this image here is an image from Meteosat, showing again where you can see these dots, there are ships. The red dots are ships that are not forming a track, and the green ones are the ones that we've identified as a ship forming a track. Now, it's not perfect, but it does a pretty good job actually of identifying these cases where the ship is actually modifying the cloud in a way that we can see. And we can then use that to map where clouds are sensitive across the Earth and kind of test the accuracy of our classifier as well. Now, we get a really high accuracy of 97%, but most ships don't form tracks. So you get a pretty high accuracy just by saying no ships form tracks. A better measure of this is the precision and recall, and we do reasonably well at those. So we get a fairly low number of false positives and fairly low number of false negatives as well. And we can also see that different kinds of ships are more likely to generate tracks. Again, perhaps as we might expect, container ships, typically the largest ships, are much more likely to generate tracks than much smaller ships because they're burning more fuel, producing more sulfur. A formation probability for container ships can reach over 30% in some regions. So if the clouds are right, it's almost certain to generate a track you can observe from satellite. Now, there are a couple of other interesting things as well that we can see. When the ships move into these emission control areas, they have to change the kind of fuel they're burning. They don't burn expensive low sulfur fuel everywhere. They switch to the low sulfur fuel when they move inside the emission control area. Ships that don't enter the emission control area don't switch their fuel. And we can actually see this in the probability of the track formation from these ships. So the orange line here are ships that don't enter the emission control area. And you can see the probability of a track formation being relatively high right up to the boundary. Ships that do enter the zone, they're kind of green and red, you can see several hundred kilometers away from the coast, the track formation probability starts to decrease, so that by the time you're at the boundary, you're burning the correct kind of fuel. There also appears to be a slight difference depending on the direction of travel, which may be due to different kinds of fuel the ships have available. Now, very quickly, we can also see these tracks over land, and these line up fairly nicely with what we know are big sources of sulfur. You can see, for example, the Scunthorpe Steelworks, power stations around South Yorkshire. Not all of these pollution sources line up with ones in the national emissions inventory, though. There are some clearly big sources of particulates here that we see in the clouds that we don't see in the national emissions inventory. So as a summary, we can use clouds, actually often an issue, but in this case, we can use them for identifying cases where ships are emitting large amounts of sulfur, which gives us a high spatial and temporal resolution. We can use these tracks to see and observe changes in the law, and we can also use them with kind of a machine learning classifier to observe ships switching fuel in detail around the edges of these emission control areas, and for monitoring emission sources over land as well. Thank you.
Thank you. And I think we've got any questions on Slido for Edward? Oh, just appearing. Ah, great. We have got one. What are the confounding factors here? Can the cloud modification be driven by water vapor from ships plus other aerosols?
So yeah, there are other potential factors that might produce trails and clouds as well. One of the nice things about seeing this change in 2015 is that it's not just the water vapor from the ships that's producing these trails, right? Because the ships are still burning fuel when they're close into the coast. They're still producing water vapor, but they don't produce these trails in the cloud. So we're pretty clear in that case that actually what we're getting is the impact of the sulfur rather than something else. Again, slight changes in ship fuel might produce different kinds of aerosol close into the coast, but it seems that from kind of our work here that it's likely the sulfur that we're actually observing.
Great, thanks, Edward. Another question. I'm going to take the third one first. Can cloud covers be too thick? I presume that's too thick.
Yeah.
For example, in the tropics?
Yeah, so not every kind of cloud is suitable for this. We typically look for kind of relatively low level clouds over the oceans, which luckily for us tend to line up with places where you get large amounts of shipping. But big thunderstorms, for example, that we see in the tropics typically don't produce tracks like this. That doesn't mean that they don't respond to these particulates, though, and that is something that we're looking into.
Great. Another one's come up, but I'm going to go for the one that came in that preceded it because we try and keep to time. Oh gosh. Can you go up on the Slido?
So this is the one about, yeah. Do you want me to just?
Yeah. Yes.
Yeah. So in terms of the pollution tracks that so the question is whether these tracks we see over the UK that don't line up with the emissions inventory, what are they from? The answer is I don't know. I've tried looking at some satellite imagery of it, and it doesn't seem to be hugely clear what they're coming from. There's no kind of secret power station in the middle of Northumberland, at least that I can see. Maybe you have some better ideas.
Well, I wonder if I can follow that up because it's. I think it's fascinating. But what kind of data would you want to overlay on your analysis to kind of try and find that? Where would you go first?
Yeah, so I mean, what I think is probably the key thing is the sulfur dioxide emissions. Typically, the sulfur dioxide itself isn't what you're looking at. It's the particulates that either come from oxidizing the sulfur dioxide or kind of that get co-emitted with it. So yeah, I suppose it's probably for trying to work out what these are. I mean, I've just been trying to use Google Earth, but I'm sure there are better ways of looking at the locations and the sources for these tracks.
Yeah, well, anyone who's got some data that they'd like to offer up to Edward, then come and find him after the plenary during lunch. Right. Edward, thank you very much. We're now moving on to our final presentation today. Again, this is looking at air quality in a slightly different way. And I'm going to introduce Daniel Potts from the School of Physics and Astronomy here at the at Leicester University to come and present this final presentation.
So yeah, hello, I'm Dan from the University of Leicester. I'm going to be talking today about smart analysis of satellite data for air quality regulators. So I'm coming towards the end of my second year as my PhD. I'm case partnered with the Environment Agency. So we're together trying to explore the potential of both current and future satellite instruments for the possibility to inform and assist in air quality regulation. Just like to touch on the fact that being case partnered with the Environment Agency means there's a big focus on knowledge exchange and collaboration. Until recently, remote sensing of atmospheric pollutants hasn't really been of high enough quality or relevant to end users such as the Environment Agency. And so there's very few channels of communication between satellite data users and developers and potential end users such as the Environment Agency or additional government bodies. But it is important to foster this sort of virtuous cycle and creates a sort of positive feedback loop so that end users can begin to explore this data and their end user needs can be fed back into future mission designs and product design. With satellite data, there's a lot of there's pros, but there's also cons. For example, they're great in the sense that they cover a large spatial extent. We're not just measuring a point source, we can cover a large area. We can monitor multiple pollutants at the same time and build up a historical record over time. And generally, for most data sources, they're free at the point of access. Some downsides are things like currently we only have 1 overpass per day per instrument. Pixel sizes are too coarse for some applications. We're looking at column counts of pollutants rather than like a surface concentration. So comparisons between the two can be tricky. And there is a high learning curve to using this type of data responsibly, which can be a deterrent for new users. We do have some new instruments on the horizon though, which will act to alleviate some of these negatives. And I'll touch on a few of these missions towards the end. So before I go on to my research, I'd just like to, I'm conscious that everyone here will be from an atmospheric remote sensing background. So I'd just like to go through some examples of where this data is typically used and to give some context of what has been done in the past. So this is probably one of the oldest examples of satellite atmospheric remote sensing, looking at the ozone hole over the South Pole, looking at seasonal and annual variations and using this to inform and evidence for the Montreal Protocol. We've also got looking at volcanic eruptions. So we can look at volcanic activity through the emissions of sulfur dioxide and also aerosol. So this is showing the La Palma eruption in, I think it was last year. You can see how the SO2 plume is transported over mainland Europe. Quite a big scientific objective of these missions is to feed into climate models to act as a constraint. So this is showing the CAMS aerosol model of showing Saharan dust being blown over Central Europe, which is obviously an issue for aviation and can constrain these models with satellite observations. We can also look at wildfires. So this is showing the Hankley Common fire this July in Surrey. You can see a clear smoke plume in the RGB view, but also in the nitrogen dioxide, aerosol, and carbon monoxide as that plume heads towards London. And the final example I'll be giving today is just the air quality story around COVID. So we saw rapid air quality improvements due to COVID-19 related lockdowns pretty much globally, giving us kind of a glimpse into a low pollution future and an idea of what could be achieved air quality wise with a marked reduction in fossil fuel based transport. So back to my research and things concerning air quality regulation. The instrument I predominantly use is Tropomi. It was launched in 2017 by ESA, and we've got data from mid-2018 onwards, so we're starting to build up that long-term data set. It boasts a 15 times improvement in resolution and a 2 to 5 times improvement in signal-to-noise ratio compared to its predecessor OMI. We get near daily global coverage, clouds permitting, and has a 1:30 PM overpass. It collects information on a range of pollutants, which makes it quite useful and relevant for air quality regulators. So this slide just sort of highlights the step up in capability we've had with Tropomi. So on the left, we can see the same day's observation for OMI and Tropomi over a large power station in Poland. And you can just see how much clearly visible the power station plume is in the Tropomi record. On the right is just highlighting how individual sites can be distinguished even in a heavily polluted area. So it's showing Johannesburg, which is in the center, which is itself is a large urban source of NO2. And then you can see all the coal-fired power stations that flank the right-hand side. You can see the individual emissions from each of those sites. So this is really a capability that we've only had with Tropomi. And so back to my research, this is sort of a list of avenues that I'm wanting to explore in the PhD, but for the remainder of the talk, I'll just be focusing on deriving emissions of nitrogen oxides. So to do this, the first step is to produce a wind-rotated aggregate. We take a daily observation such as this one and combine it with the Area 5 wind field. So we rotate this observation so that the wind vector is aligned along a common axis, and we repeat this process for every observation that passes the quality filtering requirements, which produces this wind-rotated aggregate seen at the bottom. This animation is just showing that process compared to the normal temporal average. So on the left is just averaging every observation that passes quality filtering requirements. On the right is doing the same thing, but doing that wind rotation process. And you can just see how we're getting an averaged view of the plume rather than the temporal average, which just sort of gets smeared by these variable winds. So once we've got that wind rotated average, this one on the left is for Matilda Power Station in South Africa. I've chosen this as it's a well-isolated site. It's pretty large in terms of emissions. We get a lot of cloud-free observations, and we do have up-to-date reported emissions from the site operator. So what we do is we take evenly spaced transects that are perpendicular to that the axis of rotation, which gives us the plot on the right, where each one of those lines is one of the transects. And we integrate beneath these black lines to give us our tropospheric line density. Given here, where each one of these points is the integral of one of those lines. And we notice that this has a shape of an exponentially modified Gaussian function. So what we want to do is fit this function to our line density, and it will allow us to determine some parameters that we can derive emissions from. So this is showing the function we're going to be fitting. I'm not going to go through the terms, but we're using an iterative least squares fitting approach to fit this function to our line density. So that's shown on the left here, where the black dashed line converges onto our line density. This gives us the parameters required in the top right part of the equation to derive emissions for this site. This is what's shown here, where on the left is annual emissions for Matilda, where on the left is a previous study, in the middle is our emission estimate, and on the right is the reported emissions from the operator. And we see pretty good agreement with the reported emissions within our uncertainty range. We can also look at seasonal trends. So obviously higher emissions in the winter and also a longer chemical lifetime. It's just a bit of a sanity check to make sure we're seeing an actual physical process, which we think they are. So that's great. We've got emissions from a point source industrial site. So what about when we apply this sort of method to the UK? The UK faces a number of challenges, mainly being persistent cloud cover. So any cloud contaminated scenes we have to discard, which means that over the UK, over 60% of our observations in NO2 will have to be discarded due to cloud contamination, which is obviously an issue. We've also got clusters of industry, which happen to be quite close to large urban sources because we've got high population density, so it makes it hard to distinguish between, for a regulator, if they want to regulate a specific site compared to emissions from the surrounding area. So the example we're given today is for a cluster of, there's 2 oil refineries and a power station that provides power to the refineries. on the south bank of the Humber. So we've got Hull to the north and the Scunthorpe Steelworks to the west. And this is that same animation, but for this Humber site. We can immediately see quite a big issue that, as well as the pulling from the site, we're also getting additional downwind enhancements that aren't necessarily related to the site in question. This could be from Hull or from Scunthorpe, but it's introducing noise to our site, noise to our wind rotated aggregate. And so this contamination from the sources sort of, if you look at the line density, we're not seeing the downwind decay that we'd expect to see from just a point source. So we've got additional sources, which means that we can't fit our exponential modified Gaussian function. We can't derive emissions. So this is the focus of my current work. We're looking into conditional selection methods to decide which observations to include in the aggregate, which discard. They're also looking at how atmospheric dispersion modeling may help resolve some of these issues. I'm also looking at how future missions will perform in similar scenarios. So will we have the same issues, or will the future missions be able to alleviate some of these problems? So I'll just touch on those future missions to end with. We've got Sentinel 4 coming up, which will be in geostationary orbit over Europe. Allow us to reveal the Diurnal cycle of emissions. And also crucially, although we're going to have the same amount of cloud cover, for every cloud-free day, we're going to be collecting over 10 times more observations. And so we're going to have a massive increase in our data density, which is a big factor in the quality of the aggregates. So that should help quite a bit. And we've also got CO2M, which is a high-resolution carbon dioxide sensing instrument, which also has nitrogen dioxide and methane capabilities. So high-resolution 2x2 kilometer, and is designed to improve our understanding of anthropogenic emissions. And a key part of CO2M is being able to sense both nitrogen dioxide and NO2 together, and we can look at the ratio between those two and better isolate industrial sources to urban sources. So just to summarize, in collaboration with the Environment Agency, we're designing and testing robust and auditable processing techniques with current instruments, even if those instruments themselves are not directly relevant to air quality regulation or good enough quality, so that the Environment Agency has the capacity and understanding to use future missions once they're launched. We've shown how reasonable emission estimates are possible from satellite. We just have a number of obstacles to overcome in the UK first. Thank you for listening. I'm happy to take any questions.
Thank you, Dan. Oh, thank you, Dan. Great. We have got one question so far on the slide, though. So what would the optimum spatial resolution be for your work if you had the choice?
Obviously, high resolution is always better in principle, but with these types of remote sensing missions, the smaller your resolution, the less amount of light that you're receiving into your spectrometer, so the less quality your observation will be. So you're sort of limited by the fundamental observing mechanism. So CO2M would be great with 2x2 kilometers. With 1x1, you can start seeing some urban features like main highways and stuff. So yeah, ideally, anything around the 1 to 2 kilometer range would be great for this kind of work.
Great, thank you, Dan. And as always with Slido, live interaction, more coming up. So will you be looking at other places other than the UK? Yeah, so we just did the Humber refinery site as a sort of test, but we've got this system now where we can repeat it in multiple places. So I think there's 5 different oil refineries in the UK, all around the coast. So we'll be looking at those. We originally started looking at Drax Power Station, but then UK coal power is ramping down, and so they're no longer going to be relevant regulatory sources. So we switched to oil refineries. So yeah, we're going to look at those next. And there's also like cement works, steel works. We've got Scunthorpe and Port Talbot. We're looking at all of those. We're also looking not just in the UK, but in wider Europe and stuff. So it's just going to expand from there. Great, thanks, Dan. I do feel like there's a question for the policymakers there with the possible change in energy source. What will they do if they see the analysis changing for more harmful emissions? But yeah, that's one for others to answer, not the Earth observation community. And I'm going to take the liberty of asking the last, or the second to last question. I think we've got time for that. How can the community feed into the user needs and opportunities analysis?
Good question. I'm not entirely sure.
Right. Well, whoever asked that one, maybe come back for a conversation with Dan over lunch. Great. Thank you, Dan.
Right. Cheers.
So we've got about 14 minutes before lunch for some open discussion. So I'm going to invite Beth Cole, who chaired the first session, to come up. And if they don't mind, I'm going to invite the 5 speakers from this session to come up, and if you want to take a seat at the table. And I think we've got space for one more. If there was anyone from the first session who wants to join the discussion, then they're very welcome. So I don't know whether Beth, have you spotted anyone? Miles, do you want to come out and join as well? So we've got Melanie Hutchinson with a roving mic, so we will take some further questions from the audience in the planetarium. I think one of the things that struck me is there's a lot of dependency on ground truthing and in situ data. I think I mentioned in the opening kind of introduction before the plenary 1 session that we do see kind of advancements in ground truthing data and the calibration and validation of data products through that. But I think there's still a way to go to kind of produce a standard where people know they kind of need to hit for the products that they're producing. I don't know whether there are any questions from the audience on that, or whether the panel have would like to kind of comment on that as a way of opening up the discussion. How have you felt in gathering your particularly for the agricultural use and the crop mapping? What were the barriers to really understanding the standards that were required for your products and your analysis, I should say?
I guess that I mean, one of the reasons the analysis that was presented was for places like the US was because there's actually data from the US that is sort of consistently collected and makes life easy for people. And you know, that's why you basically develop your things there. And if you go somewhere where this data isn't available, you have to go and, you know, go in fields and measure things which you don't want to do, and that makes things complicated. So, you know, it adds layers of complexity to something that is already quite a hard problem.
Thank you. Feng.
Yeah, I think those ground data are very useful, and it's very hard to get hold of those data. But I believe that I've so many studies they show they have done ground validation, but it's very hard to ask them to share the data. I think we I don't know any other fields, but in the agriculture monitoring side, I think there should be some kind of push forward for data sharing of those ground measurements, and they are quite valuable for us to validate both validate and the training. Yeah.
Great. And I wonder if Miles, who opened up with the first presentation, would like to just comment on that from a UK perspective.
Yeah, one of the main challenges we have with collecting field data is permissions, and getting permission from landowners to actually go out onto their land and collect data, which is challenging when we're trying to target specific habitats to feed into the model. Kind of, we are restricted to things like National Trust land or land that's kind of managed by Natural England as well. It's the other thing is it's resourcing, kind of getting enough people out there collecting data. So we've got a great team of surveyors at Natural England, but we're always there kind of looking for more data. But we do recognise kind of it's quite an intensive exercise in all weathers, as well as other priorities for them. So yeah, it's definitely a challenge, and it's a vital aspect of our project. And yeah, it would be nice to have more.
Great, thank you. Yeah, a real challenge to understand how we can overcome that. And Beth, do you want to ask questions, or should we go to the audience? Oh, we'll go for. Oh, right. Okay. So I wasn't sure whether that was from the last session or not, but yeah, let's see if the panel want to answer that. So, what key climates and meteorological applications can your research help with, and what improvements in satellites do you want to see improve your research? Oh, and we'll take both because it will give a selection to answer. What would your research be improved more by better resolution, data more times a day, or more accurate data? Cool, that's a big question. Who would like to answer that one?
I mean, I can start because it's kind of easy for me, because that's the direction I come from. That I'm not really a ship engineer. I mostly spend my time thinking about clouds, and actually that's where a lot of this stuff comes from, that we don't really understand that well how clouds respond to pollutants. And so ships give us that ability to experiment on clouds. So in terms of ground truth data, actually having more information about what kind of fuel the ships are actually burning is really useful. So for that, it's, you know, it kind of helps us understand how clouds behave, simulate them better in climate models. We're really lucky that we can use weather satellites for this rather than having to use kind of Planet or Sentinel. So better resolution for us is the key one, because the weather satellites don't have the resolution, but they do give us lots of data all the time, pretty much wherever you are on the globe. So yeah, I'll say resolution.
Well, I guess this question probably doesn't apply to me so much because I'm working at the upstream end with the satellite. I can say a couple of things, perhaps harking back to the previous question, is that the Gnss Reflectometry has challenges in terms of validation, because it's quasi-random where the reflections are, and they're very large areas, so the 5-10 kilometers. So you can't just put a probe in the field, that's not enough. And I think a lot of the good validation work has been done comparing it to large-scale models, but then that raises the question, how good is the model? And if a model's that good, then you don't need the satellite data. So that you uncover things when you start doing this kind of validation. And I think validation for hydro-GNSS is going to be an interesting challenge. We're wondering whether we can tap into some of the work that's being done on biomass. Coming back to this question, I think we've listed quite a few of the applications that the hydrological has climate, but it also has weather implications. The soil moisture affects the weather forecast. I think as weather forecasts improve, they are becoming more dependent on soil moisture knowledge. If you're missing that, then particularly over large land masses, then that's missing something that could be improving the long-term forecast for your weather. So perhaps that's enough from me.
Thank you, Martin. I think we'll go out to the floor for a bit. So do you put your hand up if you've got any questions for the panel? No hands yet.
Quite a generic one, which does impact policy. I'm going to take this one that's just come in. So could Daniel and others, but starting with Daniel, comment on the virtual circle with policy stakeholders?
Yes, the graphic I showed is sort of showing the key links that you need between the current developers and users of satellite data. specifically in my case, and the potential end users of the product. And in a lot of fields, this is an issue where you've got products being developed, not necessarily with a end use customer in sight. They're being developed and used by the science community, doing amazing climate science, but there's not actually a route for that to be used operationally. And so by engaging stakeholders and potential end users, having discussions with those and properly engaging them throughout the whole process, getting their feedback, integrating that into your next level of iterational or mission design or whatnot, just really helps to promote that concentration towards a goal that is suitable for both sides, if that makes sense.
And it's just had a typo being corrected. Sorry, that was said virtual circle. It should say virtuous, but I think you answered anyway. Thank you for ignoring that. If there's no more, I'm going to ask a really very generic one, and whoever feels game can go for the reply, which is about how you think we should. You're all working on how to improve the science and how you're developing ways to monitor things more effectively or better. How do we make that link, or what should be the next step to really getting that into the policy? What do we need to do to enable that link to be made, and the next step to take forward these advances and really get them implemented or get them into the process and into the stream for implementation? So anyone who feels brave can go for that.
I think the link with central climate variables is kind of been made already, that the scientists have defined the central climate variables that then feed into the Earth system models, and so that is their attempt. But I think it has to be the high level science that engages with this, so that they can see the changes that are made by a policy. So if emissions are reduced, then you expect certain changes in the Earth system models. So the linkage with Earth system essential climate variables is one way of doing it. I think it's a challenging project. I think there's a lot of very good research that we're hearing about this week that does try and make these links, but it's not easy. And I think what we heard first thing this morning about methane and carbon emissions was very eye-opening, that it's a very complex system. And so last thing you want to do is leap in and say we need to plant forests over this peatland was very short-sighted. It just needs a better and better knowledge before people can actually make these policy suggestions.
Anyone else game to chip in, or any other questions? We've got 2 minutes, so probably, yep, I think that side.
I've had a couple conversations this week where delegates have suggested that maybe one thing that can help in this space is so we have a side of existing environmental policy, right? And we're from the EO community, we're trying to help support those decisions. In any of your fields, are there, let's say, metrics where actually if legislating, let's say some new target or something new to be monitored, where that fits into the how we could help, let's say, drive motivation for the new missions and the science, but actually do something helpful. Sorry, this is a terribly worded question. Hopefully somebody picked up on what I'm asking. Are there policy drivers that should be put in place with the view of all the new EO data that we have? I'll stop there.
Does anyone want to go?
I'll just say that I think some of the things that are being discovered by some of the remote sensing satellites are uncovering new discoveries, new linkages. And I think the kind of fora like these are where the links are made. And I think that the dialogue between the scientists, the upstream instrument designers, and the policymakers, just keeping that dialogue flowing, can develop these links. So there's a great value in meetings like this for that purpose.
Thank you, Martin. We're just over time. I think on that, to answer that question, I think those in policy roles, such as myself, we need to be aware of what technology and what we're going to be able to measure in the future to enable us to form the questions that will then influence the policy. So yeah, absolutely. It's a challenge. It's a challenge for us. It's a challenge in collaboration with those in the science, both in the upstream and in the downstream. And I think, yeah, it's a real challenge that we need to collaborate on to come up with, you know, being ready to use the new data coming on board. So yeah, thank you for your question. And I guess that kind of slightly answers the Slido question that's just been come up, which is one of the key things we need from partners is more knowledge of the environmental legislation we're working to. Absolutely, we need to build on the forums for being able to, you know, partner with the scientific, you know, the Earth observation scientific community to make awareness of what the legislation is and what metrics we need. So we're now 2 minutes over. I don't want to stop you from getting your lunch. I just want to thank the panel and all our presenters. So thank you once again.